Javi, I was wondering if you could take us through some of the experimental side of gravity coming up. Now, you've worked on LIGO, and you still are working on LIGO. And what that was initially the detection of the gravitational waves from colliding black holes, but there are other phenomena that could produce gravitational waves that we, at such a scale that we can measure.
Yes, so it is very important to approach, I think, gravity from the experimental viewpoint, because whenever theory have questions, maybe experiments can even pose more questions or answer some of them, or uncover information what we were not aware. So in LIGO, we had to put on a plethora of sources. Yeah, anything which does boom or does this will generate gravitational waves. I just generated some gravitational wave for you. Yeah, very small. You can't see it, but it deformed you, I assure you. Very little.
And the shape of the room.
Yes, everything. Yeah. So we need very large masses. Yeah, and it was kind of a surprise that first we had seen fairly big black holes merging, but that was very interesting because it was not just the discovery of a black hole binary, but it was also a chance to test Einstein's gravity in a really strong field regime. Yeah, I mean around these black holes, you know, gravity is fairly violent. Yeah, so when they merged, there are kind of three phases. Yeah, one is they go around each other. Yeah, they get closer and closer to each other, and then they kind of merge, and then the final individual black hole, which was just born, quiets down, rings down, and then there will be one black hole. And this means there are three signals, yeah? Three signals carrying information about the same phenomenon. And comparing those three signals, you can actually derive a lot of information about Einstein's gravity. We were hoping to find something. We always want to find Einstein wrong, and you know the result is we always find him right. Yeah, what a tragedy. Yeah, so we did this study, and actually it was consistent with Einstein's theory. But looking at more black holes, maybe we will find a deviation. Maybe we'll find effects we didn't count on. Yeah, and there are other sources like you know, a black hole which was born is roughly as big as Long Island. Yeah, it's a fairly big one. Yeah. So a smaller black hole, which is as big as Manhattan, or a neutron star, which is a very heavy star, 1.5 times heavier than our sun, roughly also the size of Manhattan, can be eaten by a black hole. Or two neutron stars can actually kind of merge and rip each other apart and form a black hole. Can happen. And all of these processes actually test gravity on very different scales and ways. Yeah? So in a sense, the beauty in gravitational wave observation is that we just converted black holes from some mysterious, beautiful object on the sky, our pacified laboratory. Yeah? From now on, black holes and neutron stars can be considered as our backyard laboratories, when we can study the properties of gravity in a way we can never study it before. Yeah? So the discovery was, yes, a discovery. We were so happy to have it. Yeah, I worked like more than 16 years on this. I really wanted to discover something. Why did I leave if I don't discover something? But we really kind of opened up new ways for everybody. Theorists, other experimentalists, you know, there are people who are actually considering what happens when black holes eat dark matter, you know, kind of putting black holes and dark matter together. Maybe, yeah. So there are actually new ways to have experiment evidence on regimes of gravity which was not observed before, and hopefully they will give us a clue on GR or the flaws of GR. Of course, you know, quantum gravity experts will tell us, yeah, gravitational waves need big masses and will be very hard to observe, but not always.